Hi, I'm Tomas Chobola, and today I want to present our work, which is a feature-driven Richardson-LUCYD deconvolution network. What is the motivation behind our work? There are many challenges in the field of microscopic imaging. Mainly, the images usually suffer from degradation, such as blur, noise, and artifacts, which hinder any kind of post-processing or analysis of those images. There are classic deconvolution methods that remove such degradation. However, they are often susceptible to noise amplification and in some cases can even degrade the image even more. While there are many deep computer vision models that achieve impressive performance on general images and image deblurring, they often require large amounts of training data, which is scarce in life sciences, and therefore such models are not really applicable to microscopic imaging. And therefore, we propose a solution, which is a lightweight deconvolution model that embeds a classic deconvolution formula, namely the Richardson-LUCYD formula, into a deep network. And because we utilize the Richardson-LUCYD image formation formula into the model itself, the model doesn't need to learn how to form the image, and therefore it has much less parameters compared to classic computer vision models and can be learned on small data sets that can consist only of phantom shapes. And the synergy between Richardson-LUCYD and deep learning based model is that we have an efficient and effective blind deconvolution method. The image formation can be expressed mathematically through the following formula, where a sharp object X is usually blurred because of optics being slightly out of focus. And this can be expressed by a convolution with a kernel, also called a point spread function. Additionally, there is a noise or artifacts added on top of the blurry image, which can come, for example, from low exposure times. One of the classic methods for image deconvolution is Richardson-LUCYD algorithm, which is an iterative formula that in n steps estimates the sharp image X based on the blurry image Y and a corresponding kernel or point spread function K. The formula in each steps includes two convolution steps, first of which is convolution with the kernel K, and the second one is a convolution with a transpose of the kernel. Those steps can be also called forward and backward projections. In our architecture, we replace the forward and backward projections with learnable convolutional layers. And also we bypass the need for n-1 iterations to obtain the nth image estimate by estimating this image in a single forward pass with a U-shaped network. We do those steps in a single model where each step has a shared feature space with the other. And finally, when we obtain the sharp image estimate and the update step, we multiply them to get the final deconvolved image. Here are examples of results by applying our method. On the left side, there is a deconvolution of an underwater microscopic image, and you can see in detail enhanced clarity and level of detail of the biological sample being captured by the microscope. Also, the contrast of the image is greatly enhanced. On the right side, this is an example of deconvolution of a image from a light sheet microscope of a zebrafish embryo, and you can see the clarity of the details is enhanced as well, and the light diffraction and haze around the cells is greatly reduced. We also do quantitative results where we compare the method with a state-of-the-art deconvolution model such as CARE and Richardson-LUCYD network, and we do the evaluation in domain and cross-domain approaches, and in both we outperform the state-of-the-art methods with structural similarity index metric and peak signal-noise ratio. Thank you for listening, and if interested, please check our paper and code.